Alright, hell yeah. We got material mechanics, and you know what? We're going to solve this one like a G. So, and we get to use differentiation. You know, I apologize making this a 2-hour video and not even solving it right. They want to vary the area of both of these. So what we do is we do the forces in the Y. Well, only the sine component of A. So we're going to say, hey, what is A? Well, it's going to be, oh, damn it. I'm sorry. P is equal to only the sine component of A. So that's going to be A sine theta. Cool. Now once that has a pulling component, it's the cosine of A. So we're going to go A cosine theta. Well, that has to be B. So cool. So once you get this, what we want is forces A, you know what I mean, and forces B. So, well, here's force B, but it's in terms of A. So we're going to go B is equal to, oh, and then let's get A. So A, we got force A. It's just P over sine theta. So that is force A. And then for force B, that's going to be A cosine theta. So A is P divided by sine theta, and then we just multiply by cosine theta. So that this is going to be P divided by tangent theta. Hell yeah. Alright, so now we're on a roll, and this is going to be the forces in each of the members. And this is where I totally messed up, you know what I mean? Strength, okay, is in PSI, pounds per inch squared, and so that's going to be force divided by area. You know what I mean? I just messed this little equation up, and it didn't work out. So now that we got this to work out, what we're going to say is what we know the force A, we want to find the area. So let's rearrange for area. We're going to be like, hey, area of A is going to be force of A divided by sigma. Cool. And now we can do the area of A and B. And at the end of the day, we want to minimize the weight of the structure. You know what I mean? So if we have a lot of area, but the weight is basically going to be, so the definition of weight is, well, like volume times weight density. And so that's what we have. But the weight density, they said each of these bars are the same material. So we're going to say, hey, weight is proportional or synonymous with volume. So if we can just find volume total, we'll find, if we can minimize the volume of this thing, we have minimized the weight. So volume total is going to be the area of A times the length of A plus the area of B times the length of B. So guess what? Length of B doesn't change. So we're going to go length of B is equal to L. But what about length of A? I'm going to call this, so this bar is called A, this bar is called B. And so if we increase the angle, well, hell yeah. That length's going to really increase. If we decrease this to 0, it's just going to be L. So how do we do that? Well, we take L, so we take this length, and then we have to divide it by the cosine of the angle. Dividing by something small gets you that big thing. You know what I mean? So sweet. And then, what am I doing? So this is the length of A is L cosine theta. So now we have the length of B is L. Length of A is that. And now we can do the volume. So we got volume total is, oh, did we even solve for the areas? So we need to solve for area of A. That's going to be the force of A. So we got P divided by sigma sine theta. That's going to be the area of A. Now we need to find the area of B. That's going to be force of B divided by sigma. Well, that's easy. Area of B is just going to be P sigma tangent theta. Alright, hell yeah. So now, what was our equation for volume total? Area of A. So we have P divided by sigma sine theta. Now times length of A. Okay, that was L divided by cosine theta. So we got L divided by cosine theta. Alright, sweet. And then we got plus area of B. What the hell was that one? Okay, so we got P divided by sigma tangent theta. Length of B. Length of B is just L. Alright, sweet. Okay, hell yeah. So now to minimize the volume, like I got into differential equations this week. You know what I mean? I just pushed them off like no one knows differential equations, but hell yeah, we do. I'm going to try to make this short as possible, but we want the derivative. We want to take this equation and what are we going to derive? We're going to derive theta. Because if we do that, if we take dv, if we take the derivative of the volume with respect to theta, then we'll get that. We'll get something, and we're going to set that crap equal to 0. And once we do, we can find the angle, or, you know, at the end of the day, you know, you can just type this into your calculator like right now. Let's say the force is 1 Newton, L is 1 meter, and the strength is 1, you know, whatevers. So, I mean, structurally, this equation is 1 divided by sine theta cosine theta plus 1 divided by tangent theta. So let's just throw this in. So when we do the complex because I haven't done this all the way through. I just want to do a differential equation, but it might be kind of complex. 1 divided by tangent x. So now we're just going to graph this, and I have it in radians. So and now we're going to find out where, see how there's a minimum? So now we're going to trace this out. We're going to go, trace it out. So at 0 degrees, if this is 0, well, our equation don't work. So if this is 0, this thing can't take any force, you know what I mean? So like if you just have 2 bars that are totally hinged, you can't take any, you have to have some degree. So it would require an infinite amount of material, so it's nonsensical. But then once this angle gets a little bit, you know what I mean? Like, okay, it can take that force, but barely. And then so this AC member has to be friggin' huge, you know what I mean? And so you have just a thick-ass member. So then once you get up to an angle of, let's say, this minimum, see how we're getting a minimum of 0.9 radians. What the hell is radians? Like 0.5 radians is 30 degrees. 1 radians is about 60 degrees. So almost about 60 degrees, we're getting a minimum. So right now, just with our calculator, we can do minimum, left bound, right bound, minimum, and we just found our answer. So hell yeah, it's a 0.955 radians. No one knows what that is, but 1 radian is about 57 degrees. I think it's 57.3. But we do this. We go 2 pi radians, and then 360, and that converts it to, you know, normalness. So we're going to multiply by 360, divide by 2 pi, and hell yeah, we get the answer in the back of the book. That's all anyone wants. It's 54.7 degrees. Now I'm just going to trust, you're going to have to watch the end of the video. We're not going to open the back of the book yet, because what we want to do is work on our differentiation skills. So we just learned how to do some cool differential equations by scratch. And what we have here is a product. You know, we have 1 over the, so anytime that we have D, where we have U and then V like this, and I got this one memorized, then the differential is the second times the derivative of the first minus the first times the derivative of the second, all divided by the second squared. You know what I mean? The downstairs squared. So let's do this. So the first one becomes, well, what's U? I'm sorry. So we just, this is the bottom. So we go sine theta, cosine theta. And then we take the derivative of the top. Derivative of 1 is just 0. Oh, hell yeah. Our life's getting real easy. So now we go minus, and we take the top. Okay, 1, that's easy. And then we take the derivative of the bottom. Okay, that's hard, because right now we have something that looks like this. duv dx. We have the product rule. So we do the first times the derivative of the second plus the second times the derivative of the first. Even just with this one. And what, oh damn it. This is going to be a 20-minute video. Alright, hell yeah. Can we do this in under 20? So this will give us the derivative, and what are we trying to find? Well, the derivative of dv dx, you know what I mean? That bottom. So yeah, we still have to do now we have to take this as kind of a separate derivative. So it's going to be the first sine theta times the derivative of the second. I ain't explaining this today, but the derivative of cosine is going to be minus sine. You know what I mean? I'm going to explain it. I'll explain everything. Because if you have this sine of x goes like that, it's a slope of 1. So when you have an angle of 0, what gives you 1? What gives you a number 1? Well, that's cosine. So if this is sine of x, the derivative is cosine of x. Now here's cosine of x. It starts at 1 and it has a slope of 0. So what? And this is cosine x. So what equation, when you throw in 0, gets you 0? Well, that's sine x. You know what I mean? But this has a negative slope, so we do negative sine x. So the derivative of cosine, negative sine x. All right, we did it. Okay, first times the derivative of the second plus the second cosine theta times the derivative of the first. What's the derivative of sine x? Well, we just did it. It's a slope of 1. It's got to be cosine. Okay, hell yeah. So that was that. And now we multiply that up here by the negative 1. So I'm gonna carry this down. I'm gonna go minus 1. So we have that. So that's that thing. And now we have to divide it by this v squared. Well, what's the bottom? Where are we at? Okay, right here. So we have sine theta cosine theta squared. Yeah, and I'm just going to leave it like that. Because, I mean, if you did sine theta cosine theta, and then sine theta cosine theta, it's not an x plus 1 type thing. So, yeah, it's just sine squared theta cosine squared theta. Cool, so I'm just going to do that and that. Okay, hell yeah. Okay, so that was, you know, that was, what the hell, we used this on that, and then we're done. We're done with that. Okay, so now we have this, and this has to be, you know, sine theta cosine theta. Cool. Guess what? So that's what 1 over tangent is. And then we have again, we have to use this. Okay, so just keep in mind that we have that. That term's done. We got the derivative of that term. And can we clean this up? Let's see. This is a multiply. So there you go. So if this is and then we have a minus 1 here. So yeah, that might screw me up later. But anyway, so now we use this again. U divided by v. So we do the v. Okay, that's sweet. That's just easy. Sine theta. What's du? Well, what's the derivative of cosine? That's negative sine theta. Cool. And then I thought this was going to be a lot easier. But now we're going to go minus u, which is the cosine theta. And then what's the derivative of the bottom? That's going to be cosine theta. Alright, hell yeah. And then we're just going to divide that by sine theta squared. Sine squared theta. Okay, so this gets cleaned up as minus sine squared theta minus cosine squared theta. Okay, divided by sine squared theta. I can live with that. And now we're going to add it to whatever the hell this is. This is negative sine squared theta plus cosine squared theta. But now we're going to distribute a negative, so this becomes positive and this becomes negative. So now we have sine squared theta minus cosine squared theta. I'm so excited because once we get this equation, we can throw it in our calculator to see if we made a mistake, and we probably did. Why wouldn't we make a mistake? This thing's horrendous. Okay, and then we're going to go sine squared theta cosine squared theta. All right, so this is dv, derivative of the volume with respect to theta. We did it. You know what I mean? And so now we can just type it into our calculator. I have no idea if it's right or not. But we're going to go sine x squared minus cosine x squared. I guess I'm going to get some parentheses on this. And then we're going to divide that by sine x squared, divide it by cosine x squared. I like to do that. I don't like to do too many parentheses. Just divide it by that one, divide it by that one. And then add it to, oh boy, I guess I'm going to do parentheses because I hate negative signs. And then sine x, well, now I don't even know what to do. So we're gonna go minus, we're going to do minus, but then parentheses sine x squared, just so the sine part gets squared and then minus. So now we're going to go minus parentheses cosine, because I'm not fully confident in my calculator abilities. Okay, and then that we have to get parentheses on that. No, I messed up the parentheses. Whoa. Okay. So now I'm going to get a parentheses right there. So now we have minus sine x squared minus cosine x squared. Then divide it by sine x squared. There is no way we got this right. And then we're going to graph. See, yeah, holy, it doesn't even like it. Yeah, it doesn't like that negative thing. Yeah, because what's it minusing? Oh, ugly. Okay, so now I think we're good here. So, oh, it just didn't like the parentheses that I gave it right there. Oh, whoa. We have to do add it to negative sine x squared. So that there you go. Divided. So that's what we're adding. No, it didn't like it. It didn't like that parentheses. Oh, bummer. This sucks. How about we do this? Add it to 1 divided by sine x squared. And then we're going to multiply it by do these minuses go away because we're squaring them? I don't think so. Where did we accumulate these? Oh man. Okay. So we're going to go, oh, I guess just using the negative sign, I think we might be good. And shoot, I can't believe I just maybe messed up my equation. So we got out front, we got 1 divided by sine x squared. And then we're going to go negative sine x minus cosine x. So that's probably what the issue was. And then I can get rid of this divided by sine x. Holy hell. Okay, so we got a graph, and we'll see if it goes through at 0.995 or whatever. If it does, that's amazing, and I still might be under 20 minutes. Whew. You know what I mean? That would be really sweet, because I'm working on my differentiation skills. And so we're going to go value 0.9. Oh, hell yeah, look at that. So we're going to go 0, left bound, right bound, and 0.995. So this is 100% correct. You saw it here. And booyah, times 360 divided by 2 divided by pi, and 54.7. So there is an equation. I don't know how you're going to actually solve that for theta. You know what I mean? So this equation is useless because you already got the equation. You already had this equation that you can throw in and find where theta is maximized. You know what I mean? So but it's just fun to work on differentiation skills. And 1.8.1.5, we're going to look up the answer in the back of the book. And for first chapter, you know what I mean, a double star problem. This one sucked. So yeah, we have 54.7 degrees. And I apologize. I made this video and I was just like, nah, I want to use the same material. Even though it didn't make sense, because obviously this one's never going to yield. This one's never going to reach its max, but it's still going to have a fixed length. You know what I mean? So my problem still worked out, and I came up with an angle probably pretty close to the back of the book, but nah, like the way that I did it was dumb. Well, it wasn't dumb. It was just like if you bought stuff from the steel yard, you're probably going to buy the same material. You know what I mean? For that member as that member. I mean, All right, just a little bit over 20 minutes. But yeah, so I mean, this problem is kind of ridiculous because you have to vary your areas. You know what I mean? So now when you do have this 54.7 degrees, the question that I will leave for you is how messed up are your areas? You know what I mean? Could you actually could I go to the steel yard and find a cross-sectional area that matches this bar and a cross-sectional area that matches that bar that makes sense? You know, how close could I actually get if I was just going to make a shelf or whatever? So maybe I'll make a separate video on that, just because that's where I thought this problem was ridiculous from the get-go. I don't understand problems when I read them the first time through, so that's why we did that long video and just said, hey, forget about it. Well, we're just going to make them out of the same material. So, you know, for cross-sectional area will be the same, but length will definitely, and you still will have a maximum, because the question was like, well, won't this not yield? Well, sure, it's not going to yield, but you still can't have zero area, because nothing can take that tension, and so you still have to have this kind of sweet spot so the way that I did it, it still worked out, but this is the profesh way to do it. And let's not make this video any longer. Thanks for joining me. That's a video.